Yeah. Can you like just send it?
Yeah. हाँ हो तो रहा है, चेक तो करो
यार मेरे में तो इंटरनेट नहीं है।
अरे
इंटरनेट तो उसमें कनेक्टेड है।
final lecture of this semester for a really amazing topic of mathematical models of neurons under the field of complexity science. Talking about a little about the Feynman Club. So it has originally started like a reading group where the students started reading the Feynman lectures, discussing among them. Till then, it has now turned into a platform where we have eminent scholars from all across the country from our college to present their research, propoundings, and insights. That's a really enriching experience for all of us, where we get to know about what's happening in the world, what's popular in the world in these fields of the physics. Now, talking about finally, today we have our honored guest speaker, Mr. Rajat and Mishra, who is from our college only. That is really surprising for us and also inspiring. After doing his graduation from our college, he did a master's from University of Cologne, Germany, and he had an internship at computational and system neuroscience in, I think, yes, at Jülich Research Center, right? Yes. Now he is planning to do his PhD from University of Strasbourg in the complexity neuroscience field only and KT Royal Institute of Technology. Topic for today is really fascinating, but we'll be delving into the mathematical models of neurons, governing the behavior behind the neurons under the complexity science, where there are really complex networks of adaptive agents that are neurons. So without any further ado, please welcome sir to please start this lecture.
Yeah, so I think he already talked a lot about this stuff. So, this is the first final lecture of the year. I don't want to scale people away, because otherwise I don't want somebody to say here that they have a talk here, just to mark my finding of my idea. So I decided to talk very simple. First student to join. More than the technicality, we try to discuss ideas in the talk. And I would like to be as interactive as possible. Please call me as a people address me as sir. I'm not that good, right? So I would like to be as interactive as possible. I'll skip like the outline of the talk so that those of you who are not interested in certain topics will know when to go to see. So first I'll just talk a bit about mathematical modeling in general, how it works, why it's important, and so on. And then we'll look at like, a few mathematical models, three to be precise. And then later I'll talk a bit about Feynman research. Okay, so this does not work. So how did I end up doing neuroscience? So this is my master's thesis. So I was working on problem of quantum information in my master's thesis, and I was trying to study something called as well-known locality using inverse modeling. And while I was doing that, I was studying different methods of modeling binary variable systems. And I found a really interesting paper on modeling binary variable systems by some neuroscientists. And it was basically, as you will see, the neurons can also be often approximated as binary variables. Like a neuron is either firing or not firing. And I found it interesting, and then I did a course in neuroscience, and I found that interesting as well. So I decided to do an internship after my master's thesis in to see whether I actually like it or not, and I did. So now I'll be starting my PhD. But before we talk about computational science, let's just talk about like science in general. Right? So like how many of you here are university students? Okay, wow, let's start. So like, why did you guys choose science? Like, what is like the goal of science? Anyone? Yeah, okay, discover. Okay, that's pretty good. Anything else?
Understand.
Okay, to discover and to understand. That's
Fun.
okay, it's fun. That's good. It's fun. Yeah, to discover, to understand it is fun. But like many things are like science is different. So I have like a short video by Feynman that I would like play.
I'm going to discuss how we look for new laws. In general, we look for new law by the following first. First, we get Now I'm going to discuss how we look for a rule of law. In general, we look for a rule of law by the following process. First, we get it. Then we Then we compute the consequences of the guess. To see what, if this is right, if this order we guess is right, we see what it would imply. And then we compare those computation results to nature. Or we say compare to experiment or experience. Compare it directly with observation to see if it works. If it disagrees with experiment, it's wrong. And that simple statement is the key to science. It doesn't make a difference how beautiful you get this, it doesn't make a difference how smart you are who made it yet, or what his name is. If it disagrees with experiment, it's wrong. The law is good.
Okay, so Feynman says that like first step you is guess, and then there's like an offer from your right? Everybody from this one, because you would think that science is about having some sort of divine revelations about how nature works, but it's really not like that. A lot of it is just like the first step is always guessing. When you guess a lot, this guess has to be educated, and that's where the job of the scientist steps in. Now, there's a very famous paper from 1945 about the role of mathematical models. It basically says that like the most substantial part of the universe is simple enough for us to just understand like that, and that's why we need models, right? Because without models, you wouldn't be able to all the process of Feynman basically is kind of compute and then test it. You wouldn't be able to do that if you do not have a model, right? So that's where modeling comes in. In that sense, modeling is like really important to science in general, right? And often when you encounter models. In physics, honestly, they're always quite a bit confusing. But like in the other scientific fields like biology, maybe specific chemistry, models are not very convincing. Right? Like your species, like what's happening here? Like models are really great, are only great like understand, because without that, the universe is too complex for us to understand. Okay. Now, how does one formulate a model? So, have you guys ever heard of William Poplin's laser? Yeah, who has? What is it? Okay, that's not what it says. It doesn't say that the simplest range is the best, but it does talk about like a good way to start, right? So, I mean, there's a quote of this is entities must not be multiplied beyond necessity. So that models must be as simple as possible, but not simple. It doesn't say anything about simple theories being best, because that's a whole different thing. But basically, the idea is that when you start doing the model, you have to make it as simple as you can, but like not so simple that you remove all the important details, right? Now, there are a lot of other ways in which Occam's razor is justified. Like from a practicality perspective, your model has to be simple for it to work. Otherwise, you won't be able to solve it. And then there's also philosophy of science. So there's this famous philosopher called Karl Popper, who's talking about the philosophy of science, which, by the way, is something really interesting, and all science students should at least familiarize themselves with. So in this case, science has to be falsifiable, not verifiable, it has to be falsifiable. And if you have simple models that give simple results that can be falsified, right? So there are multiple ways of like justifying Occam's razors, like why you should always try to make that simple as possible. Another reason, something defined here is aesthetic. There was this belief, especially before the 20th century, that nature is beautiful. So your laws or models that you write out, there's something aesthetic about it. But like nowadays we are So this is a very popular joke that I think some of you might already know about. It's a very popular book in environmental problem solving. That and this is like a spherical cow is not worth again and again. So this is like from that book. So the joke basically, for those who are not aware, is that farmer decides to go to a university to increase food production, and they decide to set up a committee which is led by a theoretical physicist. Why they would do that, I don't know. And the theoretical physicist of farmer is the first thing the first statement that the theoretical physicist is right? And that's a joke that this is sort of simple things. Except that it's not really a joke, like that's actually what we do, right? Now this approach might sound absurd, and in fact it might even sound offensive to people who as the biography somewhere. Yeah. To an expert who has labeled log into the cloud that we do is spherical very safely, right? And that is something that like you often face in science, that like you have these computer scientists, physicists that come up and make models, and then biologists or I don't know, ecologists, they have worked really hard to find out what the specificities for the system, and then come and say that okay, look, all of these things actually don't matter, and it's just a sphere, so it's just a point in some cases. That's how it is. The key is to understand when there are details which you can ignore, right? And for that you have some understanding of the question that you're trying to ask, and what is your aim behind asking that question. So here are some famous models. You guys know them. So what is the first model? The first equation. Oh, okay. Okay, I just. Oh, but I think statistical mechanics is not in the 6th semester. So this is the easing model, which is perhaps the most popular model in statistical physics. The easing model is just to explain the emergence of ferromagnetism. Right? So the easing model assumes that you have these binary spins that that are, let's say, on a graph or a lattice, and the neighbor ones. So the summation here implies the neighbors, and the neighbors interact with some Popli Jij, and then there's also an external field H happening there. Now, at its core, the model includes many things, right? Like because materials are very complex, magnetism is a very complex phenomenon. There's quantum, there's all sorts of quantum interesting quantum mechanics happening there, and you guys people do quantum mechanics to solving really difficult questions, but easy model ignores all of that quantum mechanical aspects, and it just says that okay, let's just say that there is some reason there is a Popli Jij that sort of forces systems to be together. Right? So it's a very good example of what a model is. It is a very successful model because it is. I mean, there are many variations. Right? You know what the second model is? The one with SI. This one. You know what this model is? No?
SIR.
Okay. 3 years ago, this model was becoming really popular, but not very popular. This is the SIR model. It's a model of basically how diseases spread, and SIR model is a simplest model. And I remember that like the past was immediately after me denying and who are even studying this model quite in detail, and even took data from like to see how basically this is spread. So yeah, basically 3 years ago when Neuron first came out, every firm they can hire who knew how to code was everybody was making their own version of SIR model. There were modifications of it. That is, so basically what you do is that you take your population and then you compartmentalize your population into groups, right? In the SIR model, it involves the susceptible, the infected, and the recovered, right? And but then you can keep adding more groups. You can have people who are exposed but not infected yet, and so on. And you write dynamical equations, differential equations for how these compartments will evolve. And it is, I mean, yeah, it has not been very successful, and a lot of governments were actually hiring epidemiologists to solve different versions of the SIR model to understand better ways of controlling epidemics. Right? Now this model, not everybody is about it. Is there anything from Max here? So this is the operator plane model. It's called the Neuron model, and basically it's an ecological model that describes how the population of the predator and the prey will evolve. Provided the predator dies naturally and needs the prey to survive, whereas the prey sort of just I mean the prey has its own dynamics that's independent, but it's affected by the predator because the predator needs it. And you can see that there are really interesting oscillations because whenever the prey population peaks, immediately after that the predator population also peaks. But then the prey goes down, and then you have these oscillations. So like neither of them are extinguished, but like they oscillate. Right? So again, this is a very popular model. Now this last figure. Have you guys seen this figure before?
It's a strange retractor.
What?
Strange retractor.
Yes, this is a retractor. Most popular, this is the retractor of a system called the Lorentz system. It's the most popular. I mean, you might have heard of the butterfly effect because the retractor is like a butterfly. So initially, this model was described. I mean, Lorentz group is not discovering atmospheric convection. But since then, this model has become like the paradigmatic example of nonlinear dynamics. So yeah, basically, models are everywhere, from physics to geophysics to ecology, everywhere. And now, before we finally start discussing what we're talking here about neurons, I'll start with a caveat. This is by very famous physicist called George Box said, like, whenever you build a model, you have to always remember that they're all wrong. So it's important to not overextend your model. That is, be confident about aspects of your model. But like a good scientist knows when the model will not work and when it will work. Right? And that's where science lies. It lies in, at least as a theoretician, your job is to figure out first of all what goes in my model, what would be right, where it would work, and where it would not work. Right? Okay. Now let's go to modeling in neuroscience. Before that, do you guys have any questions, comments? So, modeling in neuroscience, we basically say there are 3 broad types of models. Like the border between these different 3 broad types is very fuzzy, it's not set in stone. So, the first kind of models would be descriptive models. So, as the name suggests, descriptive models will just try to describe what's happening. Right? For example, somebody takes EEG, you know what EEG is, right? It's not just brain waves and measures. And somebody will take a model to describe the oscillations of EEG. Now, for this person, the brain is sort of like a black box. They just know how the data comes and they will just try to make a model to describe that. And then there's mechanistic models. This is where like a lot of physics comes in. Right? So mechanistic models would be about describing how something happens, but like with the understanding of biology, so how that is not so clear, right? Like for example, how it is. I mean, we will see in the detail. So mechanistic models try to describe the exact mechanism, as opposed to descriptive models, which is trying to describe how the data is. Okay. And lastly is like the interpretive models, where we try to sort of interpret what really is happening. Right? So in terms of neuroscience, these interpretive models are usually some sort of models that try to understand how the brain forms things like computation, information processing, because that is the brain's goal, right? And the thing is, the biology is so complex that if you start actually modeling biological things to understand information processing, you get into that. Right? So interpretive models sort of do that. They try to understand all these information processing and such things. That's where because it's interpreting what is basically happening. Right? Now, when we model a system, there are different scales which you need to be aware of. So in neuroscience, we have multiple scales. I mean, not just in neuroscience, basically any field of science you can do in there are different scales. Even when you do physics, you wouldn't use quantum mechanics to solve a problem in, I don't know, hydrodynamics. Right? So different scales, you can give there different scales. So you have first of all the molecules, and the molecules play a very important role in the brain. There are special molecules that are evolved to form specific functions for the brain. Then there are these things called synapses, which are basically places where neurons can be. I mean, I will come back to synapses later. Then there are basically compartmental models which try to basically model neurons. Our focus for most of the talk here would be on neurons, so like how do we model neurons. And then you have as a network. So basically, when you're modeling things as a network, you basically ignore all about how your neuron looks and you start model neurons as points in a network. And this is a very popular approach in neuroscience and also in artificial intelligence. So this I'm trying to think about the word, but this is called connectionism, which is basically the idea that all cognitive processes that you see are basically a result of like how things are connected, right? And it's what the whole neural networks move about. Basically, also neurons is like points, and it's the connections between them that matter, and the way of these connections. We'll come to that later, and we'll see how what things happen. And then you can have maps, or then you can have systems. So basically, you take brain areas as one compartment in your system, and then you try to make it. And then of course you have larger dimensional models, right? So different scales of organization that one works in, and there are people from, let's say, theoretical physics, maths, and computer science working on all of these scales, from the molecular level to the large level. And what I really like about neuroscience is that it really brings in a lot of people from different fields together, from engineering, from chemistry, from physics, from bio, together to work like at different levels of this organization. Right? Okay, now let's talk about neurons. Before that, I think it's nice to give a little historical overview. So this is Johannes Müller. He was a really popular. So this is Johannes Müller. He was a really popular physiologist. I've written the year wrong. It's not 1980. It's 1800 something. But basically, so at this time there was some idea that yes, there is electricity inside the body. But the thing is, there were still a lot of people who were refused to believe that electricity is what is causing these things, right? So, like for a lot of people, there was like a very hard boundary between biology and physical sciences like physics. You know, they believed in something called as vitalism, that life has this vital force that simply cannot be explained by physics and use numbers, right? But eventually, we found out that at the end of the day, it's still physics, electricity that had. Right? So, basically, this. So. So there were many people who had who sort of thought that electricity is present in biological systems. Like the oldest example I know is of this Islamic philosopher Ibn Rashid, who basically said that the force that like an E uses is almost the same. It's the same as the force that attracts iron to a magnet. So, but he didn't quantify it very well. But over time, he said in the 200s, basically electricity was this new thing and it was really trending. It was a fashionable thing back then, and there were lots of people doing their own experiments with it. So Galvani and Mishra, they first, so I think it was an accident. They accidentally gave electrical impulses to a dog's leg, and they saw that the leg moved. And then this was very interesting. People started replicating these experiments. Galvani is the guy who Galvani meter his name. And then Volta, which I think a lot of people know as physicists. Volta was he sort of acknowledged that yes, there is electricity can cause movement, but even he sort of refused to believe that electricity is the normal thing that causes movement. So he thought that yes, electricity can cause it, but that must not be the natural mechanism that is happening inside the body. So he thought that the actual mechanism is something else, right? So, and Volta was like a pretty big guy. So again, that brought things down a bit. But later, there were more students that with better and better technologies, we were able to detect fine electricity. So, Emile Dubois, who was actually a student of Müller, funnily, he made a really sensitive galvanometer, and he used that sensitive galvanometer to detect electricity in neurons. He tried to excite neurons using chemicals, using electric impulses, and every time he excited them, he noticed that the galvanometer was needle shot up, right? So, he noticed this. Finally, Julius Bernstein, he did the same thing, but he amplified it quite on a finer time scale, and he noticed these spikes. And this is what we believe is the first thing of something called as action potential. An action potential are basically the spikes that neurons have, which they use really. Right? Lastly, in the 1950s, in this guy called Edgar Adrian, that showed that the Newton is all or nothing principle of neurons. Where, so by this time we knew that there are spikes, but Adrian showed that neurons spike, and the length of the spike does not depend on the stimulus. Right? So basically, if there is a higher stimulus, all that will happen is that the frequency of the spikes will be more. The length of the spike does not change. And that's actually a pretty interesting thing that makes modeling easier for us, because we cannot model out as zeros and ones, because the output is not changing, it's just the frequency that will change. Right? So Edgar Adrian was the first one that came with this all or nothing. Right? Now, talk about neuron a lot and probably modeling, because I will be using some words, it's important to know what those words mean, right? So, neuron, I mean, not all of them look like this. This is like a prototypical neuron. So, there is this area in the center, it's called a cell body or soma, which has the nucleus and the mitochondria and all of these things. And then there are these things called dendrites, which are sort of the input terminals. So dendrite take inputs from other neurons, and then the cell body sort of processes them, and then axon is the output, but it's really thin and long. Usually neurons have many dendrites, but then the axon is a single one that later branches out and gives other neurons to synapses. Synapses are the junctions where neurons communicate with each other. Right? Now, neurons based on their function, you can see Right? For example, this is neuron, cortical, pyramidal neuron from the cortex. This has many dendrites in one action and like different kinds of dendrites. We will encounter this neuron again using the form. And then that is a fertility neuron in the cerebellum, and it has like over 100,000 dendrites and 100,000 inputs, but like just one output as nice. And then this is another type of neuron called the stellate cell, which is also found in the cerebral cortex, and it provides basically inhibition. But yeah, the other part of this slide is just to show how different neurons are and how their architecture is important. We will come to that. So one more thing that this is important to understand is that so cell membrane. Now this is not specific to neurons, this is specific to biology. People who have done good biology in high school might know this already. Basically, the cell membrane consists of a lipid bilayer, right? So there are so you can basically see these like round circles with like tails. So that's basically a lipid molecule. It has a hydrophobic end and a hydrophilic end. And there are two such layers which basically form the boundary, and this boundary is selectively permeable. It allows things to go through and does not allow things to go through. Ions are not one of those things that it allows to do, right? So ions that have to travel have to go through something called an ion channel, which is something like an as a pole. This is a very rough diagram. An actual ion channel is super complicated. And this is what consists of it. So ion channels basically help ions pass through. And there's another thing called an ion form, which is not sure this figure. An ion form basically uses ion channel just allows ions to pass. An ion form is something that uses the energy to basically push ions out or in. So it's an active process. It uses their energy to do something. So that's the ion form, right? So now we've understood this basic architecture of neurons highlight. We can look at the simplest models of how neurons fire. So the simplest model is leaky integrated fire neuron. And so you basically assume that the cell membrane, it basically acts like a resistor, a circuit, as shown here. And you assume that there is an external current that's being supplied to the circuit. And the membrane has some resistance, some capacitance, and the membrane also has something called as a resting potential. The resting potential is the potential of the difference. So, across the cell membrane, what happens is that negative ions are inside and positive ions are outside. So there is a voltage difference across the cell membrane, and this voltage difference is called the resting potential. Okay? So, basically, the most simple model would be just make a circuit like this, with a resistance and a capacitor and a battery, which will be value resting for the resting potential. Right? Now you can basically write equations, because we know how charges on capacitor behave. We can Q equals Cv, and we know how the current is. So you can basically write an equation connects currents with this. So if you have done EF, it's already would already be familiar with this type of circuit, right? This is called an RC circuit. And what does an RC circuit do? I mean, second year students must have done the TSO experiment, right? So an RC circuit integrates, and which is an experiment that you must have done. And so the neuron also is sort of like that, except that there is an active this thing and there is an external current as well. Right? Now this equation is a very simple equation, right? It's just a linear ordinary differential equation that's very easy to solve. Right? I'm assuming everybody here knows how to solve such an equation, right? Now you can solve this equation for various. Remember how the equation looks? Maybe I will just write it down, because then I'll ask you what the answer should be now. When I is equal to 0 and let's say you have some initial neuron, how would the equation look? Like how would the dynamics going to happen? Anyone? So I mean this is equation, and I is 0, what happens? It's very simple, right? It's a very simple differential. Is it a constant? I mean there's a variable here and then there's a variable here. So what happened? I mean, just okay, do a variable substitution. Substitute minus us something. What is the result of an equation like this? In second or third years at least. It's a differential equation. It's the same differential equation as it's just an exponential decay, right? I mean, so it's an exponential decay, right? Except that there is no pressing. Now, so basically, that is when there is no external current and you have some finite potential, it will just decay to its value. Right? I don't know why you guys are so confused about that. Whereas what would happen in the other cases, I mean, for that you would have to solve them. Which you don't have to find. So yeah, this is how sorry, so that's your plus sign in the first expression that I think I actually used. Yes. So when there's no current, it would just there is an exponential term that will decay with time constant tau. Tau, by the way, I mean some of you know this already, but tau is time constant. It's the product of R and C, and that will dictate how fast it will decay. Now, if there is an external current, then you have a term like that, and your dynamics basically would take a value depending on the external current and the US. So initially to some. Whereas if you have time dependent input, then what is basically happening is that an integration happens of the current. So depending on your time, you will get some. But this is just the dynamics of the equation, right? Remember that we talked about neurons, they spike. Right? So now, how do you make them spike? So in integrated coil neurons, the usual idea is that you put in the spike in your model explicitly, right? So you say that there is a threshold value pH, and whenever u reaches that threshold value, there will be a spike. Okay, and once the spike happens, your u will actually automatically go back to the resting value, and then the same thing will be repeated again, right? So basically, like the u that is your potential across the membrane, to follow this equation, until it's threshold UPH, and when that threshold is reached, it will fire a spike, and after it will just go back to UR, and then if there is still current, the same thing will happen, right? So here I have. So this is a very simple code to implement. I mean, this is a very simple equation. You can solve it for all of your own people of doing that. And here is how the result looks for constant external current that is high enough. So when the external current is high enough, then you need the external current to be high enough for there to be a spike. Otherwise, external current in this point. Otherwise, there will be no spike. So if there is a constant external current, you see that there are spikes at like regular time intervals, right? Because with constant external current is basically being integrated, it reaches the threshold value, then there is a spike, and then after it goes back, and then the same thing happens again. Now, let's say there is an exponentially decaying one. Right? So here is exponentially decaying current, but I was estimating I put the time constant is too large and it decays too fast. So it doesn't. So the current is not large enough to reach the threshold. So the neuron sort of. I mean, it increases initially, but then it goes back to the resting value because the current is still resting. Then if you have something like a sinusoidal external current, then you get a behavior like this. So it's a very simple model. You guys can try to code this on your own, or you can just Google integrated coil neurons, and you will actually find that there are already codes there, and you can play around, give different sorts of external current and see how the neuron responds, how the spikes happen, and so on. Now this is a very basic model that just talks about spikes and stuff, but it still has a lot of features that are desirable despite its simplicity. which is also generalized model. So this is a generalized version of the created file where we basically replace this with some sort of function and you take the resistance as a time dependent function. Okay. And then usually what is done is that the function f of u is chosen to be of this kind. Why do you think so? What is so? Let's just look at it. So let's say you have the equation du by dt equals f of u, and your f of u looks like that. What can you say about the system then? I mean, just be loud. It's okay if you're wrong. I mean, it's fine. Nothing. Okay. So do you guys know what fixed points are? Yes or no?
Yes.
Yes, but some of you don't know. So fixed point is basically the point at which the derivative of the distribution is zero, right? So one thing that has to be you have to do is that when there is no external current, your function's fixed point should be resting potential, right? And when there is an external current, your fixed point can be something external. Now in this case, based on your choice of f of u and r of u, you can get a lot of interesting behavior that you can. Basically what you desire, right? So like you have some data and you want to mimic that data and you can choose blocking functions f of u and r of u such that you can reproduce the same spikes that you are found in the data. Okay? So let's just see how created file works. Here are two examples of generalized created file neurons. So the first one basically has a quadratic term added to it, increase the complexity, and the second one has an exponential term added to it. You can now do more things. You can make the equation stochastic, and so on. Okay. Now, leaking created files, despite the simplicity, are super useful. For example, here is a paper from 2011 that basically tries to understand Parkinson's. So Parkinson's has these oscillations that you will find in your brain, and the paper basically models about 3,000 neurons, and basically 3,000 neurons of this kind are connected in a network to sort of understand how oscillations happen in Parkinson's. So even a very simple basic model that does not really take a lot of understanding of the neuron. I mean, all you had to know was that there is a membrane that basically acts like a circuit, and you wrote an equation like that. But even that can actually give you a lot of insight, right? Now let's move on to a better, more complicated model. So before that, any questions? No. So now let's talk about the Boston function model. It's a very popular model for which Boston function won the Nobel Prize. So they were one of the first people to actually record the action potential in the game. And what they actually found is that in action potential, so that is the action potential are the spikes that we've been talking about all this time. They found that once you become spikes, there is actually a rebound. Where it actually goes instead of going back to the resting value. It goes to a value that is less than that and then it goes back. So these people were the first ones to notice this form of the action potential. They did that in 1939. They were both visualists by training. But after they did that, Hitler invaded Poland. I'm connected, but basically they were sent off to war. And when they were sent off to war, both of these physiologists ended up gaining some technical skills. So they were working in radar. I think maybe Hodgkin was working in radar and Huxley was working in feedback control systems. So basically when they came back from war, these people were physiologists by training, had some technical skills. So then they designed really nice experiments that are really landmark in neuroscience, where they basically try to measure the sensitivity of different ion channels in the membrane of the giant axon of an animal called the squid. And based on that, they formulated a mathematical model for it, basically explain how this would happen. And it's honestly, it's one of the best examples I know of bio-making maths in the world, because it's both done by the same person. A lot of serious experiments and a lot of rigorous mathematics, and they try to make a model, maintain data and everything, and then they finally came with what we now call as the Popli model, which is the landmark of neuroscience, and they likely deserve the Nobel Prize for that. So yeah, so this is how the model looks like. So basically, once again, you have a membrane just like that, but it knowledge of the fact that there are two types of ion channels in the membrane: sodium channels and potassium channels. Sodium channels allow sodium ions to pass, potassium channels allow potassium ions to pass. And actually, there are multiple types of ion channels, but in their model, there are just two. and they had and each of these ions have their own potentials, which are Nernst potentials. So, how many of you remember what a Nernst potential is from 12th standard? No one? What's Nernst potential? So if you have a concentration of ions in like regions, Nernst potential basically tells you what would be the potential because of this concentration gradient. So each of these ion channels have their own Nernst potentials. And in addition to all these ion channels, there is another additional leak current, which is sort of similar to what was there in Popli Memorial model as well. Right? So yes, so they have a concept like that, this like that. Now the key point here was that unlike in the leaky integrated file, where your capacitance resistance was constant, here what they notice that the ion channels, they are sensitive to voltage. That is, there are points when the ion channel is open and points when it's closed. So to model that, they added variable resistivity in their model, and that's shown as that. So the arrow basically indicates that the resistance varies, and then they basically remove mathematical forms for all of that. Right, so this is a term by term. The first term you all know, that's the term due to capacitance. The last term, Vm minus K, is the same as the term that we had in the leaky integrating file here. And it's the same as this term, except that G is now because tau is 1 by RC, and if you take R here, you get conductance. Okay? So the first and last terms are clear. The second and third terms basically describe the conductance of the ion channels, and they introduce what they call as gating variables to describe the behavior of these ion channels, because the ion channels are voltage dependent. So for the potassium channel, they introduce a variable n, and they say that the n evolves with time like that, and then they introduce a variable m, which they say evolves like that, and then h. So m and h control the sodium channel, and n controls the potassium ion channel, right? And they evolve in time, and then they dynamics. This is a sort of complicated equations, but again, this is nothing that you guys cannot do. I mean, I'm sure at least the third years by now know how to solve coupled equations. Excluding student then. They also do a lot of precise experiments found out how the behavior of these parameters, alphas and betas. So alphas and betas are just parameters that control the dynamics of these gating variables, and they found it to be like this. And based on that, the dynamics that they were able to do something like that. So their mathematical model was able to accurately find the behavior of the action potential, which looks like this. So there's a spike, and then there was negative gain, and then it starts to increase again. Whereas this is the behavior of this is the behavior of the gating variables. So around the time of the spike, n increases. Now n is the gating variable that controls the sodium ion channel. So basically, the sodium ion channel is open near the time of the spike, but then it slowly decreases against it closes. Whereas the potassium ion channel slowly increases after the spike. Right? So potassium ion channel is responsible for this stabilization and this depolarization. So this increases due to the sodium ions entering, and this increases due to potassium ions entering. Okay. Here is a biological diagram of what happens. But I will come back to this later if I still have time. Okay, so until now, what we discussed was first we saw the integrated file. There's basically a simple model of how spikes are generated. Then we look at the how spikes can be generated using a simple model. Then we look at what's the model that like incorporate knowledge about the biophysics of neuron and convert them to differential equations to generate spikes. In this model, we did not add spiking explicitly. We did integrated file, we said that you have to spike once you use the threshold, not here in the Popli model. Now let's go to the third type of model that we discussed. This is like the interpretive models, like where we try to study information processing capabilities of neurons. Okay. So the first people to sort of do that were basically vector effects. They put this paper called the logical calculus. So they try to they basically interpret neurons as being capable of performing Boolean operations. Right? And how do they do that? So their model is something like that. Right? So the neuron basically receives a bunch of inputs, and then basically it then sums all of these inputs up. And then if the sum is above a certain threshold, that neuron will fire 1, or that neuron will fire 0. But neurons can be both excitatory or inhibitory. So to account for inhibitory neurons, if any of the neuron is inhibitory, then you have to out 0. And so this is a very simple model, but then we try to show that this can actually perform standard Boolean operations. Right? Like for example, let's say you have to perform the AND operation. Right? So let's say you have a neuron with 2 inputs, and you have to perform AND. So basically, now your threshold for what will be, you would want to fire when both of them are 1. So that means the threshold will be 2. So you sum them up, the threshold is 2, and if it's greater than 2, then it's not 1, or it's not 0. Similarly, for OR, your threshold would be AND. For OR, your threshold would be 1. And similarly, based on like different logical operations, you can figure out what the threshold should be. Right? So it was a very simple, simple model. They tried to show that neurons are capable of logical operations, and the logical operations are basically equal foundations of two very different systems. So neuron can do that. That's how the brain works. Right? Then they gave this model perceptron, which is like, I would say, the ancestor of all of machine learning we see right now. So in the recurrence neuron, what we saw is that what the neuron does is that the neuron sums all of its inputs equally, except if they are inhibitory ones, which in this case it will just not function. But it sums all of them and then it just outputs. But there is some mechanism of like learning. It's like, and also it gives equal weightage to all of these sums. Right? The perceptron does not do that. This is what the perceptron does. So in perceptron, usually with all the inputs, but the perceptron sums them in certain weights. That is, it will multiply every input with the corresponding weight and then sum it up. And then usually there is also some sort of bias that is included. And then after that, we have a hard limiter. That is, now all the sum that it has done, it will basically check if that is more or less than a certain value, usually 0, and then it will output plus or minus. Right? So the advantage of perceptron here is that like there are different weights because the tasks that perceptron perform are much greater than tasks that we call it weights right? So how do you create perceptron? So one very popular rule of learning and your science is heavy learning, which is basically summarized in that sentence, neurons that fire together. So which means basically two neurons that are firing at the same time are more likely to be connected to each other. Right? So heavy learning works very simply. Let's say you have NS training samples, and then you have some input vectors. Input vectors basically describe what the input of the previous neuron is. And then you have some desired output. Right? So heavy learning, so this is an example of something called supervised learning, where you know what your output is, and you want to train your network to use that output. So once you have desired output, you compute this quantity, this the average of 5 times x, and you say that the weights are just that along the scaling factor. So it's something called as one-shot learning, where you don't actually learn over time. So you just because the fire together basically says that if they're firing, then they're probably more likely to be connected. So that's why you define your weights as this factor. So it's taking output and then the cross correlation. So what would this do now? So let's say if some neuron, let's say the jth neuron is 0, so minus 1, when gamma is 1. So that means that weight would be basically when they hit state, your W would be less for that neuron, the weight would be less for that neuron, and then the route of state would be more. So that's how it implements the fire together, right? Is that clear? Yes. Okay. Good. But the thing is, this does not take into account the performance of the network, and it's just one-shot learning. It does work in some cases. I mean, the main advantage is that it happens in one step, but you can do better, right? You can actually train perceptrons. So the guy that you do perceptrons, Rosenthal also do this perceptron thing. Where you basically update your weights based on your desired output. The desired output is y upon m. So m here is an index. I put it on top to. So when I refer to sample, I would put the index on the top, and I put the component of a vector, I would put the index on the top. So M here is the index, not the power. So this is the desired output for the nth sample, and then the output of neuron takes the input, and then what output it is. And you see the difference, and based on that difference, you update your weights along with some learning parameter epsilon. Right? This is very nice, it's a very concise tool. And there is a theorem, it's called positron convergence theorem. It basically guarantees that this group will converge for linearly separable inputs. So what are linearly separable inputs? Linearly separable inputs are basically inputs like this. So let's say your inputs that are in a high dimensional space, you can draw a hyperplane that, so basically all your inputs have outputs either plus 1 or minus 1, right? If you can draw a hyperplane that properly separates these plus and minus 1s, then your positron is said will converge. So you're guaranteed to converge. Otherwise, it will not converge. Okay? So that is the drawback of positron. But despite this drawback, the positron was still quite successful, at least for a while. But then something happened. There were these people who decided to analyze the mathematics of positron learning in detail, and they found out that the positron could not actually do many tasks. So initially there was a lot of optimism when the positron first came out, including to the point where people figured out that this is how the brain works. But it turns out it wasn't the case. And one very good example of this is the XOR problem. You guys know what the XOR problem is? So XOR problem is just like a gate. So it's like and then and except when both the inputs are 1, 1 to 0, 0, the output has to be 1. Otherwise, your output, if they put it, then your output is 0. Right? So this is the XOR problem, and the positron cannot solve the XOR problem. Right? And then this was a dip in research of the positron. But then, actually, we come to the 10 later. But despite this, the positron, at least in some areas of the brain, the positron is a good model of learning, right? And that area is in the cellular. So, if you remember one of the 3 cells that I showed, one of them was the Popli cell, that cell which had a lot of inputs but just like one output. And basically, it has been found that the positron model is a very good model of learning for the Popli cells, but not for the overall brain. Right? So basically this was the story of the positron, and its moment of theory, but then we found out that it's not as universal as there was a black plate it was bit in research. Until that is the 1980s, when Jopé and his collaborators came up with something called as backpropagation. So basically what they figured out was that in a positron, which is yes, this is a positron, which is one layer thing where you have your inputs and then you have an output. If you add more layers, you can actually do more tasks. Including the XOR problem can actually be solved by just adding one more layer. But you can keep on adding more and more layers, and then you will be able to do more and more tasks. Now the thing is, initially also people had conceived the idea of a multi-level positron, but they thought that it did not show a lot of promise because what if positron doesn't work, how would that work? But these people, and again another landmark people, came up with a method called backpropagation, something that is still the most widely used method in machine learning, to basically train multi-layer positrons. So your simple positron group that you had here would work for one layer, but for a multi-layer positron, what you do is to calculate what the error is basically this difference, and you backpropagate it. And Feynman and his collaborators gave that result in their paper. And so that basically renewed interest in neural networks. And over time, as you guys know that, like as data became more and more available and picking up became more and more improved, people started making bigger and bigger networks, and now you know where we are. Now machine learning has become its own thing. Different from neuroscience, initially positrons and their aim was to introduce how the brain works, but now every team uses machine learning for its results. Now here this is a very recent paper from Neuron, where they actually found that, remember the neuron that I showed you in one of the first slides, the cortical pyramidal neuron? It's basically found that those neurons are capable of many complex tasks. And this paper basically showed that, not this paper, there were many other papers that showed the same thing, that a single neuron in many instances acts not like a positron, but it actually acts like a multi-layer positron. Which is kind of crazy to think about, because like you have these machine learning models with like large neural networks where each node does something, but like in the way it's like each neuron in itself is a multi-layer neural network, and that is embedded in the network. So sort of like allows you to appreciate the enormous computing power of the thing, right? So now how is it that a single neuron can actually act as a multi-layer perceptron, because you would assume that there are dendrites cell input, and then there is the cell body, and then there's an axle, right? So you would assume that one single neuron would act like a perceptron, but then it turns out that dendrites are not passive entities, right? So in a passive entity, dendrites would be something like that. They all bring the input to the cell body, which processes it and gives the output. So something like what a perceptron is. Except that it has been found that dendrites are also active sites. That is, they're not just postmen delivering letters, but they also do their own organization and stuff. Sorry, not organization, processing and stuff. And that's why a single neuron can actually act as multi-layers, which is crazy. So, I mean, this sort of like includes the things that I wanted to talk about neuron, right? So, look at like 3 different ways of modeling the neuron. So, the first one was very simple leaky ingrained neuron. It sort of just was a very basic model of the membrane as a survey, and then you put an external point, and then you explicitly ask it to stop, and then you adjust the parameters of your model and you use this one. Then you have the constant complexity model to know information about the biophysics of the network and the field. To give a model where you do not have to explicitly ask it to spike. You know, the dynamics of the model itself causes the spike. Lastly, we look at kind of models that are completely different from these two kind of models, because where the aim is to study information processing and computation. And we first look at a basic one, but like a quick neuron, then we look at a perceptron, and how a single neuron in certain areas of the brain can actually act as a perceptron, but it is actually capable of much more. It is capable of forming computations at a multi-layered perceptron. Right? So that sort of summarizes the things that I want to talk about the neuron. Do we still have time? No? Okay, that's fine. I mean, I also want to talk about for a few things, but I think this is a good place to stop. Questions? Yeah.
So when you said that it is active, can you expand what exactly is it active on? Like what is happening there?
Oh, so in electronics, an active passive so a passive component is basically something that does not add energy of its own. Whereas an active is something that actually sort of adds on energy system. So that's where the word is borrowed from. So a passive dendrite will just pass along the information. Whereas an active dendrite will actually process that information and then pass it.
So process in terms of what? Like
Processing in terms of what? Okay, then so to understand that is question, like to actually understand like the exact molecular mechanisms of how it works. But that's not the point of the model here. The model here is just to say that like, it can actually act as that. But the answer really lies in the precise molecular mechanisms that allows even the dendrite to actually process information and not just act like a carrier. I would assume that we will branch dendrites, but neurons actually show a lot of adaptability. Neurons adapt really fast, and we have actually done, there are multiple experiments that show us that neurons can actually. So now they adapt much faster than this. So maybe an active one can be more faster, but I would not say so. So basically, like, with my understanding of this is that like evolution has created things in a very specific manner. Like, so like neurons are optimized for like tasks that is specific. So the way the neuron is say the visual area of the brain, so not for neuron that is so memory, based on that maybe to have active dendrites. But I don't know. Maybe they can. Any more questions?
this might be a trivial one.
There are no trivial questions.
So you mentioned that there are two. I think in the Hawksley model or the one prior to it, the resistance they had a variable, right? So what depends? How does it change? What changes it? This
So
one.
you talk about this, right? Yeah, so basically, what happens here is that I can give you like one explanation for how something like this can happen. So basically, that resistance corresponds to the currents of sodium and potassium, which are regulated by the ion channel that is open. Now, this ion channel itself is voltage sensitive. So depending on the voltage, it will actually change. Now, let's say we are applying an external current, it will sort of change the voltage. And let's say the ion channel, which is, let's say, some sort of complicated protein, undergoes a sort of structural phase transition, where it sort of ends up opening. So that's how these transitions work. So all these, so in biology you have multiple, so ion channels are everywhere in biology. They basically, and the principle is that as you change the energy, it goes from one structure to another structure. So the stability of the structure is the ion channel opens. And once it opens, now the resistance is different. So now the resistance is less because ion channel is open. So that's why the resistance is available. But that was not it. Yes. And a bunch of other things. Everything. But in this model, you would say that is a sort of point on modeling, right? Because even these ion channels, they are extremely inhomogeneous. Okay, there are multiple kinds of ion channels, there are multiple kinds of ion channels for different ions. Like in this model, also have this look at just assuming that two ion molecules, two ion channels is actually good enough. Okay, then I guess I will let you guys go. You do seem tired.
Another one before I leave. So you're trying to model the neurons themselves, right? So is it possible, I don't know what I'm coming from here, so is it possible to actually model the memory? Like, I don't know how memory works, memory of a person.
Yes. So there are models that model memory. Usually they do not model it at neuronal level, but more at the network level. So there is something, for example, like a very basic one is something called as a Popli network. Popli network is an example of something called as a recurrent neural network. I told you about the word before. So a recurrent neural network, forward neural network has these layers that go ahead, but a recurrent neural network has these loops that come back. Right? Popli network is basically like an example of a recurrent neural network. And basically what happens is that the Popli network that equals to dynamics and it has fixed points. Okay? And those fixed points basically has memory. So that is one example. But like there are also other kinds of for example, working memory is the transient memory that you have. For that there is a different kind of model. But like there are these network models that are used to most of them involve some version of a recurrent neural network.
Thank you, Jacob sir, for being here. Thank you, all of you. This is the time for refreshment now. Please join us.
अच्छा बाहर
So we'll have a group picture outside. Let's come.
Live off.